Okay, so this session is going to be mainly a review session for tomorrow's test. We have quite a few of the questions, as you can see. Some of them are from the book for chapter 27, the things you went over Monday. This one is going to be mainly about capacitance, electric field, and potential energy. So let's get into it. Okay, so you have two squared planes, one carrying positive charge, density of sigma, and the other is negative charge density of negative sigma. They're separated with distance r. Find their electric field. Okay, so let's start with drawing them first. Oh, that was not what I was expecting. Well, okay. Okay, so if this one has positive charge everywhere, and then there's negative plane in here. That has negative charges in it. So if it looks from the side, it'll look like this. Those are the two. One of them being positive sigma has a charge density sigma, and the other is negative sigma. Okay, and we'll assume that both of them have the same shape. So the first question is, we want to find what's the electric field between them. So first question, where would the electric field point? What's the direction to the electric field? Is it going to be to the right or to the left?
Would it be to the right?
Yes, indeed. Okay. But then simply I would ask you, do you know what's the equation of an infinite plane? Like this generalized equation of an infinite plane? What is E equal to? Well, if you don't know, the equation for a plane in general is sigma over 2 epsilon. So since that will be the electric field produced from one plate. So since we have two, and both of them have sigmas, and both of them pointing in the same way, you can say that the E total is just equal to just double it. 2 epsilon is just going to be sigma epsilon. Okay, so is that okay?
Is the sigma the same as the like fancy N in like our notes?
Okay, so sigma mainly means like the total charge on the plane over the area of the plane. That's what it means.
Okay, thank you.
Okay. So then the next question would be, what would be the potential energy of this system? What would be the potential energy? So in general, what is the potential energy U equal to? So in general, the potential energy is equal to Q E dot R. Okay, so what we can do is we can look at the potential energy from the point of view of this one, of like the positive charge plane, once we have the negative charge plane comes to it. Or the other way around, because both of them would be the same. So we would have, if we were looking at the point of view, like as this is standing still and the negative plane is going from infinity to it, so then this Q would be the Q of the negative charge plane, which we have here sigma as Q, total Q over A. Since both of them like are the same shape and the same thing, that means they have the same Q. So then that just means that this Q would just be negative big Q multiplied by E, which the E we had, which is sigma epsilon multiplied by R. But we can expand this a little bit. We have Q is equal to Q over A. So it's going to be negative Q A epsilon naught R. It's negative Q squared over A epsilon naught R. Is that okay? So is that okay with everyone?
Yeah.
Okay. So then, it should be down there. Okay, so what is the electric potential difference between them? How can we find that? What is delta V equal to? What is V in general equal to, or delta V in general is equal to?
Field times distance.
Yes, you can put it as the electric field, the negative of the electric field. It's the integral of ds. But yeah, since we have E here constant, we can then just put like since E is constant along between the two plates, you can just take it outside the integral. So then V will equal to negative E, the integral of ds. And ds here is just a straight line. And if we set this as being the origin, and we know that the distance between them, like this distance is r, and we set this as being the origin, so then it would just equal to the integral from 0 to r. It's just simply equal to negative ER, which we have E is equal to sigma epsilon naught. Let's put that in here. So delta V is equal to negative sigma epsilon naught multiplied by R, which is going to equal to negative Q R over A epsilon naught, which if you see is the same as the E we have except for Q. And there's also like another formula for, like, we have the U is equal to QV. So that also means that V in itself is equal to U over Q. So again, if we were looking at the point of view from the positive plane, then we would have the U equal to negative Q squared R epsilon naught, A epsilon naught divided by Q. And this is the charge, this Q represents the charge of the negative plane, just again, big Q. So the Q's will cancel. That's negative Q R over A epsilon naught. So is that okay?
Yep.
Okay. So now we're trying to find the capacitance between those two planes. What's the equation for capacitance? C. What is C equal to?
Q over V, or delta V, I guess.
Yes, indeed. So it's going to be Q over delta V. So we have Q divided by negative Q R over A epsilon naught, which I'm trying to believe, it's going to believe that this negative is external. We'll see where it came from. So it's going to be Q multiplied by A epsilon naught over negative QR. Q's would just cancel. Have A epsilon naught over R negative, and this negative is extra. We shouldn't be getting this negative. Okay, so let's see. Where did it all go wrong? Okay, so that means the potential difference is actually positive, because here, if we look, we have a positive charge and a negative charge. So, oh, well, then it depends where we're looking at. If you're looking from 0 to R, it should be negative Q. We're fine, I think, yeah, like we're fine. The negative is just arbitrary for your reference frame. Like if you change your origin to be here, the negative should go away. Okay, so no, we're good. Okay, so now we're looking at just gonna redo the same thing, but now we have some input to put in, like some numbers instead of just variables. So to find the electric field, we can just use it as big Q over A epsilon naught. Okay, so do we have Q? We do have Q. So have E is equal to Q A epsilon naught is going to equal to Q NC nanocoulombs over the area, where I said that the side is 1 meter. So the area will be 1 meter cube squared epsilon naught. And that will equal to Yeah, it will equal to 564.7. And what are your units for electric field? It's Newton per Coulomb. Okay, now just trying to find what is the potential energy in the system. That we say is going to equal to negative Q squared R A epsilon naught R over A epsilon naught. And just in case you're wondering what is epsilon naught equal to, epsilon naught is equal to 8.85 10 to the power of negative 12. Okay, so just plugging that back in, the negative 5 nanocoulombs multiplied by R, where we have R is equal to 2 centimeters. It's going to be 0.02 meters over 1 squared, and epsilon naught again. So that's going to equal to 11.29. And what is your units? Does anyone know?
Joules per coulomb?
Not quite. It's just joules. Because if you looked here, we have U is equal to QE dot R, where E itself, like where, okay, so we have the units of E is equal to newtons per coulomb. So then when you multiply QE, this coulombs goes away. So now it's only going to be Newton, which is, again, the definition of force. Force is equal to QE. So that means when you have QER, oops, the units of that is equal to newtons meter, which is work, which is again equal to joules. So the potential energy will equal to joules, just joules. Okay, so let's find the V. The V is equal to negative QR over A epsilon naught, which is equal to, again, negative 5 nanocoulombs. What's the difference between these two? Okay, well, I did a mistake. This should be squared. That will be squared, so that will be equal to negative 5.647. Just negative 5.6 10 to the power of negative 8. Okay, for this one, be negative 5 nanocoulombs multiplied by R, where R is again 0.02. A is 1 squared, then epsilon naught. That will equal to, that's what we had before, being the negative 11. 0.29. What is the units of V? It's volts. So it'll be just also V. Anyway, for C, the capacitance is going to equal to negative A epsilon naught over R. Epsilon naught over R. So that just be negative epsilon naught over 0.02, which is going to be really, really, really small. Epsilon naught over 0.02 to negative 4.43 10 to the power of negative 3. What are the units of capacitance?
Is it farad?
Yes, yes indeed. Which we just put as F. And this is also not negative 3. This is negative 10. I don't know why I go negative 3. Okay. So yeah. That'll be question 1. For question 2 and 3, I took them from the book. I thought it would be a good idea. Like for those 2 questions, I wouldn't really know the answer right away. So it would be a little bit fun, or thought it would be a little bit helpful to see how even I don't know the equations, what to do so I can get the answer. So just looking at the question. So if we have 10 to the power of 16 electrons flow through a cross-section of a silver wire in 320 microseconds with a drift speed of 8 to the power of negative 4 meters per second, what is the diameter of the wire? So that's just by what we have here. So the number of electrons we have is 1 10 to the power of 16. We have time, where it's 320 microseconds, which is also 320 10 to the power of negative 6 seconds. We also have drift speed equal to 8 10 to the power of negative 4 meters per second, and we need to find what is the diameter. So a simple thing we can do is we can just go to the book and try and find an equation that have all of these. If it loads first. There we go. Okay, so just cruise along. You can find the first thing that we have, that the number of electrons is equal to IE, which would be the current multiplied by the time. Okay, that would be a thing. Then a second thing would be the electron current is equal to NA/VD. Okay, that looks like a promising thingy we can deal with. Then also, again, the question, it says it was a silver wire, and here it gives us a table with the electron density of silver. So let's use that first. Okay, so there will be a missing thing we need to know. So we have the density of the electrons are 5.8 10 to the power of 28. 5.8 10 to the power of 28 electrons per meter cubed. Okay, so we need to find what is the area, or like what is the diameter. So first of all, we have IE is equal to the number of electrons multiplied by the area multiplied by the drift speed. Okay, so we do have the number of electrons. We do have time, we do have V. Okay, so this is one equation that we have. There's also another equation that we saw along the way, being this equation that the total number of electrons is equal to the electric currents multiplied by time, change in time. So we also have big NE is equal to the electric currents multiplied by the time. Okay, so the first question, this big NE is the number of electrons that passes. Okay, which do we believe it would be this one, so this one is small n, it's a big N. Okay, so we roughly have everything we need. We can now find IE, and we can then find the area using the density. So let's just start with what we have. So to find the electric current electron current will be equal to the total number of electrons over time. So there will be 1 10 to the power of 16 over 320 10 to the power of -6. Plugging that in, that will give us 32 10 to the power of -6. A big number. 3.125 10 to the power of 19. Okay. So now we have 3.125 125 10 to the power of 19 is equal to NE A or VD. So let's just first check what is the small NE is equal to. So the small NE is the number of electrons per cube meter. That really sounds a lot like density, I would say. So that then means this is the small NE. Okay, so we just need to find what's the area, and with the area we can find the diameter because it would be a circle. So let me actually draw what the thing will look like. Okay, so there will be electrons in it. And what we need to find is what is this D equal to? And that'll be really easy to find because the area, we do know that the area of a circle is equal to pi r squared, where the r itself is d over 2. So d over 2 squared, that will be the area. But first, let's just find what is the area is equal to. So if we rearrange this one, we would have that the area is equal to 3.125 to the power of 19 over NE, where we have NE multiplied by the drift velocity speed. Just plugging everything in. have E is 5.8. Multiplied by 8 to the power of -4. Now equal to really small number. Yeah, that would make sense because we have a huge number of electrons down there. That's going to equal to okay, so it's going to be 6.7 to the power of -7 meter cubed. That also is going to equal to pi d squared over the 2 squared, which means that the d is equal to 6.7 to the power of -7 multiplied by the 2 squared over pi and the square root of that. That should give us, let's see, square root of all of that. (9.26 to the power of -4 meters, which is roughly 0.9 millimeters, which you can just say is also roughly equal to 1 millimeter. Okay, so questions? Does everyone understand what I did here? If not, you can unmute yourself or just type in the chat which part was not really clear to you. Okay, so let me just go over that once more. Okay, so the question gave us the number of electrons flow through the cross-section area of a silver wire. So if this is the wire, it gave us the flow number of electrons that's passing through it, which should happen to be 1 to the power of 16. And that is the big NE. And also gave us how much or how long did that take. Like for those number of electrons, it gave us 320 they took 320 microseconds. And they also have a drift speed of just 8 to the power of -4, which we have here. Then we know it's a silver wire, so we can find what is the density of electrons in it, which what I did when I looked in the table over here. So look at the silver is 5.8 10 to the power of 28 electrons per meter cubed. Then, using the equations, I found that in general, that the electron current is equal to the density multiplied by the area multiplied by the drift speed. And also, we found that that the number, like the electron flow, is equal to the current multiplied by time. Because in a way, you can say, like, this number tells you how many electrons are flowing per second. So if you have this, you can find the total number of electrons like flow through this cross-section area, through the cross-section. So we have the number of electrons that flee already and the time it took them. So with these, we found IE. Then we have another equation that's saying that the current is equal to the density number, the electron density multiplied by the area where they are crossing, which is being this area. Oops. Multiplied by the drift speed. So what we need to find in a way is the area. So to divide everything that we have except for the area over the electric current, which gave us what's the total area of the wire, and then just using, we know that the area is equal to pi r squared and r is equal d over 2. We were able to find what d is equal to. Okay, so moving on for question number 3. This is 27.6. I will add that. How many conduction electrons are there in 1 millimeter diameter gold wire that is 10 centimeters long? Okay, so be a little bit something similar. Need to find, we can first find. Okay, so again, we do have another wire. This time it's gold. And there are electrons running through it. Before we start this, we need to find everything that we can. So it gave us that the diameter is 1 millimeter. Diameter is 1 millimeter. That means that just straight up we can find what is the area of that wire. So the area again is equal to pi d over 2 squared. That will equal to pi 1/10 power of -3 for 2 all squared, and that will equal to okay, that will be 7.85 10th power of -7 meter cubed. Okay, and we can also, since we know it's gold wire, we can easily find what is the electron density in it. Okay, so gold is 5.9 10 to the power of 28, a little bit higher than, actually quite higher than silver. Okay, so have the Ne of gold is equal to 5.9 10 to the power 28 electrons per meter cubed. Okay, so how many conduction electrons are there in 1 millimeter diameter gold that is 10 centimeters long? Okay, so let's see if there's any other equations that we can find. Oh, that would be more for second parts. How far must the sea of electrons move to deliver? Yeah, it feels this can be for something else. Well, anyway, okay, so how many conduction electrons are there in the 1 millimeter? How can I find that number? Does anyone know? Okay, so this number that we got is telling us how many electrons in volume. And we do have an area, and we also have like depth in some sense. So with the area and the depth, we can find the volume of the wire. And if we just multiply it by the density, it will give us the number of electrons that are available to run around. Okay, so with the AV is equal to A, it's called D, depth would be 7.85 10 to the power of -7 multiplied by 0.1 meters. That will equal to meters squared Okay, so that means that the number of free electrons that can run, number of free or conducting electrons is will be the NE times the volume. So 5.9 to the power of 28 multiplied by 7.85 to the power of -8. That will equal to was it 28 or was it 29? That I do believe close 29, 28. Oh yeah, okay, still 28. Never mind then. So we would have 4.63 10 to the power of 21 free electrons just running around in this wire, which is a huge number. I mean, it's say the next question, how far must the sea of electrons? It's not overstating, it's actually a C number of electrons. Okay. So how far must the C of electrons in the wire move to deliver a -3 nanocoulombs of charge to the electrode? Okay, so any ideas? Does anyone know? Now we have the number of electrons that are free to move. How far must they move to give us negative 32 nanocoulombs of charge to the electrode? Okay, so let's see. Let's see what we can find here. Charge carrying a current, carrying wire. Nope, that's not what we need. Well, we can look at it in a different way. If you don't really have anything ready in mind, we can say this way. So those electrons are just what? Are just point charges. So each electron is just as a point charge, negative point charge. Right? Now what is the equation of an electric field? The equation of electric field is equal to K Q over R. So I want to say, how far must the sea of electrons in the wire move to deliver negative 32 coulombs of charge to the electrode? Actually, I don't know. Because to me, it seems like if I have this number of electrons, this in itself will give me a charge as the charge of an electron. Like 1.6 to the power of negative 11. So if I have 4.63 10 to the power of 21 multiplied by 1.6, was it? 10 to the power of negative 19. That's in itself is equal to is equal to 741.4 coulombs. Huh. Why does it say how far? Okay, well, I might not really know the answer of this question. Does anyone have any idea what to do?
I think I have an idea on what to do.
Yes, please.
I think you find the number of electrons, and then you set that as Ne, or capital Ne, and then you want to use the formula that lowercase ne times the volume equals uppercase Ne, and then you solve for H.
Oh. Okay, so I have Ne is equal to what?
Well, capital Ne equals the charge times or divided by the amount of electrons per charge, or times the amount of electrons per charge.
Okay, so the amount of electron per charge. Okay, so now we do have the number of electrons in here. So how can we use that?
Yeah, so you calculate the number of electrons, which is 1.99 times 10 to 11.
Okay, I'm a little confused. When you say 1.99
okay, so
10 to the 11, what is that?
Okay, so you have negative 32 nanocoulombs of charge,
Yes.
and then you times it by the conversion factor 1e over 1.602 times 10 to the negative 19 coulombs, and then from there you
Okay,
can.
so I have this and divided by what?
Okay, yeah. So you have the charge there, and then you want to divide it by 1.6 times 10 to the negative 19 electron or E per coulomb.
Okay.
Like you basically
Okay,
just
so
need to find the number of electrons.
well, we already found it in here in the first part.
But not for the negative 32 nanocoulombs of charge.
Okay. Okay. Okay, I see. Okay, now I see what do you mean more.
So it's like how many electrons you're pushing through and then how many have to come out. I may be wrong.
Oh.
I did.
Okay, so like okay, this in itself is giving me we need 2 10 to the power of 11. Okay,
Yeah.
well,
So that's how
yeah,
many electrons you get.
electrons.
And
Yeah.
then you can say that capital NE equals lowercase ne times the volume.
Okay, so capital NE is equal to the small ne over the volume.
Times the volume.
Times the volume, okay.
Because the meters cubed would cancel out.
Yes, indeed. Okay, well, that's what we found. That would be the NE, big NE, right?
Yeah.
Okay.
So then you can say that volume is equal to the area times the depth, or however you called it.
Yeah, we did
Then
find
from
that.
there you can solve the depth.
Okay, so we already found what is the volume.
Yeah, but this is a different. Like you're trying to solve the length.
The other way around?
Yeah, but now you have different
Oh.
values.
Okay, I see. Okay, so now, oh, I see. So now instead, I want to find what is the depth of those stuff.
Yeah.
Like, what's
If you have a certain amount of electrons, what's the depth that they take up?
Okay, well, that's a little bit twisted question. Okay, well, thank you. We'll try to do that then. Okay, so yeah, okay, so we do have this as being the big NE, and big NE is equal to small NE multiplied by the volume, and we have the small NE is given to us, so that means that the volume is equal to big NE over small NE. That will be just 2 to the power of negative 11. I moved the negative as its electrons, so they already have a negative charge, over 5.8 to the power of 28. That will equal to 5.8 to the power of 28. 3.44 to the power of negative 18. Okay, and that will be our volume. Oh, it's not right B because it just means potential. That will be meter cubed. Okay, and we do have our area is equal to, well, the area is equal to 7.85 to the power of negative 7, which can equal to V over D, which is being how far we need to find the sea of electrons. So that means our D is equal to V over A, which is 3.44 to the power of negative 18 over 7.85 to the power of negative 7. That will equal to 4 4.4 to the power of -12 meters, which is really insanely small. That will equal to, so like equal to 4.4 to the power of -3 nanometers. Okay, so is this what do you think? How it should
Yeah,
go?
that's what I got too, but I'm not 100% sure if it's right, but it makes sense to me.
Okay. Well, does anyone have any other thoughts? Because I honestly don't know. Well, okay, I'll stop recording for this part.